calming journey through cosmic emptiness. Let yourself settle in for a moment. Find that comfortable position where your body can truly relax, where the weight of the day begins to lift from your shoulders. Take a slow breath, feeling the air move through you, and as you exhale, let any tension drift away like smoke dispersing in the evening air. Tonight, we're going on a journey through the cosmos, but not one that requires any effort from you. Just close your eyes if you'd like, or let them rest gently on a distant point, and allow the story to unfold around you like a gentle tide. We're going to explore something so vast, so incomprehensibly empty, that it challenges everything we think we know about the universe. But don't worry about understanding every detail or remembering every number. Let the words wash over you, painting pictures in your mind of cosmic landscapes that stretch beyond imagination. So breathe, relax, and let's drift together into the depths of space, where the biggest void we've ever discovered awaits, and where we found something hiding that shouldn't be there at all. The discovery. A quiet revelation. On an ordinary day in 1981, in the quiet halls of the University of Michigan, an astronomer named Robert Kirshner was conducting what he thought would be routine analysis of galaxy data. He wasn't searching for cosmic mysteries or looking to overturn our understanding of the universe. Kirshner and his colleagues, Augustus Omler Jr., Paul Schechter, and Stephen Schechtman, were simply trying to create a three-dimensional map of the cosmos, measuring something called redshift to determine how far away galaxies were from Earth and how they were distributed through space. Redshift is a beautiful and simple concept at its heart. When an ambulance races past you on the street, you hear the pitch of its siren change as it approaches and then moves away. This is called the Doppler effect, and light does something similar. When a galaxy moves away from us, its light stretches out, becoming redder, shifted toward longer wavelengths. The faster a galaxy recedes, the more its light shifts. And because the universe is expanding, more distant galaxies are moving away from us faster than nearby ones. So by measuring how much a galaxy's light has shifted toward the red end of the spectrum, astronomers can calculate its distance. Kirshner's team was painstakingly measuring the redshifts of hundreds of galaxies in a particular region of the sky near the constellation Boötes. Boötes, pronounced Bo-O-Ts, is named for a figure in Greek mythology, the herdsman who eternally drives the plow, which we know as the Big Dipper, around the North Celestial Pole. It's not one of the most famous constellations. It doesn't have the recognition of Orion or the visual drama of Scorpius, but it contains Arcturus, the fourth brightest star in our night sky, a brilliant orange giant that has guided navigators and inspired poets for millennia. As the data accumulated, as each new galaxy's position was plotted in three-dimensional space, a pattern began to emerge, or rather, a lack of pattern, a gap, an absence. In the region they were surveying, there should have been galaxies. Based on the average density of the universe, based on what they saw in surrounding regions, this volume of space should have been populated with hundreds, perhaps thousands, of galaxies. But as they looked at their data, as they checked and rechecked their measurements, the team realized they were looking at something profoundly different. An enormous region, roughly spherical, where galaxies simply didn't exist in the numbers they should. The center of this empty region sat approximately 700 million light-years from Earth. To put that distance in perspective, imagine standing on Earth and looking up at the Andromeda Galaxy, our nearest large galactic neighbor, which sits 2.5 million light-years away. Now imagine a distance 280 times farther than that journey to Andromeda. That's how far away the heart of this void lies. But distance was only part of the story. The real shock came from the void's size. As Kirshner's team traced its boundaries, they realized this empty region stretched approximately 330 million light-years across. 330 million light-years. The number is so large, it becomes abstract, losing all connection to human experience. But let's try to grasp it anyway. Our Milky Way galaxy, home to somewhere between 200 billion and 400 billion stars, stretches about 100,000 light-years from edge to edge. That means you could line up 3,300 Milky Way galaxies end to end, and that chain would equal the diameter of this void. Picture that for a moment. Take our entire galaxy, every star you've ever seen in the night sky, every nebula and star cluster, the entire spiral structure with its graceful arms of stars and gas, and then imagine more than 3,000 of them arranged in a line. That's the scale of the emptiness Kirshner's team had discovered. When they published their findings, they gave their paper a wonderfully understated title, phrased as a question, "A million cubic megaparsec void in Boötes." A megaparsec is a unit astronomers use to measure cosmic distances equal to about 3.26 million light-years. A million cubic megaparsecs is a volume almost impossible to visualize. The paper described what they'd found with scientific precision, noting that one plausible interpretation of their data was that the region was nearly devoid of galaxies. But in conversations, in hallway discussions, in the informal language that scientists use when they're not writing for journals, people began calling it something else. The Great Nothing. The Great Void. Names that captured the profound strangeness of what they discovered. Initially, Kirshner's team found just one galaxy in this vast emptiness. A single spiral galaxy, lonely beyond measure, floating in an ocean of nothingness. They called it, with a touch of poetry that astronomers sometimes allow themselves, the loneliest galaxy in the universe. Imagine being that galaxy, if such a thing could have awareness. Imagine looking out in every direction and seeing nothing but darkness for millions of light-years. No neighboring galaxies, no clusters of fellow travelers through space, just your own stars and the vast, empty dark. Of course, the void wasn't completely empty. As other astronomers turned their telescopes toward the Boötes region, they found more galaxies hiding in that immense space. By 1987, just 6 years after the original discovery, astronomers had found 8 galaxies in the void. By 1988, 3 more. By 1989, 15 more. And by 1997, the total stood at 60 galaxies. 60 galaxies in a region of space that, based on the average distribution of galaxies in the universe, should contain approximately 2,000. Think about that ratio for a moment. The void contains only 3% of the galaxies it should. It's as if you walked into a city that should have 1 million people and found only 30,000. The emptiness is profound, statistical, undeniable. And yet, even more mysterious than the emptiness itself was the arrangement of those 60 galaxies. They weren't scattered randomly throughout the void. Instead, they were arranged in a rough tube or cylinder, running through the middle of the void like a thread through a bead. Why would galaxies arrange themselves this way? What could cause such an unusual distribution? These questions continue to puzzle astronomers to this day. The discovery of the Boötes Void was, in retrospect, one of the first clear signals that the universe had a structure far more complex and interesting than anyone had imagined. Before Kirshner's survey, astronomers knew that galaxies clustered together. They'd identified groups and clusters of galaxies, regions where these island universes congregated due to their mutual gravitational attraction. But the idea that the universe also had enormous, empty regions, vast cosmic deserts where galaxies simply didn't form or survive, was new and strange. The Boötes Void earned another nickname that captured its mystique, the Great Nothing. It's a name that resonates with something primal in human consciousness, the fear and fascination we feel when confronted with emptiness on a scale that dwarfs comprehension. In a universe filled with stars and galaxies, with matter and energy, with light and activity, here was a place defined by absence, a cosmic silence, a void in the truest sense of the word. Kirshner himself went on to have a distinguished career, becoming a professor at Harvard and contributing to one of the most important discoveries in cosmology, the accelerating expansion of the universe, work for which two of his former students won the Nobel Prize in Physics. But his discovery of the Boötes Void remains one of those foundational findings that opened up an entirely new way of thinking about cosmic structure. It showed us that to understand the universe, we need to map not just where things are, but where they aren't. Understanding cosmic emptiness. When most people hear about a void in space, their minds might conjure an image of complete emptiness, a region of perfect blackness where absolutely nothing exists. This intuition isn't entirely wrong, but it also doesn't capture the subtle reality of what cosmic voids actually are. To understand the Boötes Void, we first need to understand what we mean when we talk about emptiness in the context of the cosmos. The universe is not uniformly filled with matter. This might seem obvious when you look up at the night sky and see the gaps between stars, but the non-uniformity extends to scales far beyond individual stars. Galaxies themselves are not evenly distributed through space like sprinkles on a cake. Instead, they form an intricate pattern that astronomers have come to call the cosmic web, a term we'll explore in more detail shortly. For now, the important thing to understand is that voids are an integral part of this structure. A cosmic void is a region of space where the density of galaxies is significantly lower than the cosmic average. Notice that this doesn't mean there are no galaxies at all, just far fewer than we'd expect. The Boötes Void, with its 60 galaxies instead of 2,000, is an extreme example of this underdensity. Most voids are smaller and less dramatically empty, but they all share this characteristic. They are regions where galaxy formation was suppressed, or where galaxies that did form were somehow pulled away to denser regions. To truly grasp how empty the Boötes Void is, let's build up our understanding of cosmic scales step by step, starting from the familiar and working outward to the incomprehensible. Begin with Earth. Our planet is tiny on cosmic scales, just under 13,000 kilometers in diameter. Light, traveling at its incredible speed of about 300,000 kilometers per second, can circle the Earth more than 7 times in a single second. Our planet, which feels so large to us in our daily lives, is a mere speck in space. Now zoom out to our solar system. The Sun sits at the center, with Earth orbiting at a distance of about 150 million kilometers, a span we call an astronomical unit. Light from the Sun takes about 8 minutes to reach Earth, the outermost reaches of our solar system, where the influence of the Sun's gravity finally gives way to interstellar space, extend roughly 1 light year out. The distance light travels in a year, about 9.5 trillion kilometers. Take another leap outward. The nearest star to our Sun, Proxima Centauri, sits about 4.2 light years away. If you could somehow travel at the speed of light, which physics tells us is impossible for anything with mass, it would still take you 4 years and 2 months to make that journey. At the speeds our current spacecraft can achieve, the trip would take tens of thousands of years. Now we arrive at our galaxy, the Milky Way. This magnificent spiral structure, containing between 200 and 400 billion stars, stretches approximately 100,000 light years from edge to edge. Our Sun sits about 26,000 light years from the galactic center in a minor spiral arm called the Orion Spur. To cross the Milky Way at the speed of light would take 100,000 years. All of recorded human history, from the first written records in ancient Mesopotamia to the present day, spans only about 5,000 years. 20 times the length of all human civilization would pass before light completed its journey across our galaxy. The Milky Way is not alone in space. It's part of what astronomers call the local group, a collection of more than 50 galaxies bound together by gravity. The largest member of this group is the Andromeda Galaxy, which lies about 2.5 million light-years away. On a clear, dark night, far from city lights, you can actually see Andromeda with your naked eyes, a faint smudge of light in the constellation Andromeda. That smudge is actually the combined glow of about 1 trillion stars, a galaxy larger than our own Milky Way. The photons entering your eyes when you look at Andromeda began their journey 2.5 million years ago, when our ancestors were just beginning to use stone tools. The local group itself is about 10 million light-years across. It's a modest collection of galaxies, dominated by the Milky Way and Andromeda, with the rest being smaller dwarf galaxies. Our entire local group is gravitationally bound, meaning these galaxies will remain associated with each other for the foreseeable cosmic future. In fact, in about 4 billion years, the Milky Way and Andromeda will collide and merge, creating a new, larger galaxy that some astronomers have already nicknamed Milkometa. But even the local group is just a small neighborhood in the vastness of space. Zoom out further, and you find the local group is part of the Virgo supercluster, also called the Laniakea supercluster, a collection of about 100,000 galaxies spanning 520 million light-years. And this supercluster is itself just one structure among many in the cosmic web. Now, finally, we can begin to appreciate the scale of the Boötes Void. At 330 million light-years across, the Boötes Void is more than 30 times the diameter of our local group. You could fit the entire collection of galaxies that makes up our cosmic neighborhood, the Milky Way and Andromeda and all their companions, into the Boötes Void more than 30,000 times over and still have room to spare. Let's try another comparison. The distance from Earth to Andromeda, that 2.5 million light-year span that represents our nearest large galactic neighbor, fits into the Boötes Void 130 times past. If you could somehow stand at one edge of the void and look across to the other side, even traveling at the speed of light, it would take you 330 million years to cross. When the light now reaching us from the far side of the void began its journey, Earth was a vastly different place. Primitive plants had just begun to colonize the land. The first insects were evolving. It would be hundreds of millions of years before dinosaurs would walk the Earth. The void is so large that astronomer Greg Aldering made a striking observation about it. He noted that if the Milky Way had been located at the center of the Boötes Void instead of in our current position, we wouldn't have known there were other galaxies until the 1960s. Think about what that means. For all of human history, all of our philosophy and art and science, we would have believed we were alone in the universe. The night sky would have been filled with stars, all from our own galaxy, but there would have been no fuzzy patches of light that turned out to be other galaxies when viewed through telescopes. No spiral arms of distant island universes, no clusters of galaxies, no cosmic web. Just our galaxy, and beyond it, darkness extending for millions upon millions of light years. In reality, we discovered other galaxies in the 1920s when Edwin Hubble used a 100-inch telescope at Mount Wilson Observatory to resolve individual stars in what we now know as the Andromeda Galaxy, proving it was a separate galaxy beyond our own. But if we'd been in the Boötes Void, even our most powerful telescopes in the 1920s would have seen nothing but emptiness beyond the Milky Way. It would have taken decades more of technological advancement before we could have detected the faint, distant galaxies at the void's edge. This is what emptiness means on cosmic scales, not the absence of all matter, but the absence of the structures that define the universe as we know it. The Boötes Void is in the truest sense a cosmic desert, a Sahara of space where travelers might wander for millions of light years without encountering the oases we call galaxies. And yet, mysteriously, 60 galaxies do exist within this vast emptiness. These void galaxies, as astronomers call them, are among the most isolated objects in the universe. The average distance between galaxies in the Boötes Void is about 10 million light years, compared to typical intergalactic distances of about 3 million light years in more populated regions of space. These void galaxies are, in a very real sense, cosmic hermits, separated from their nearest neighbors by spans that dwarf entire clusters of galaxies in denser parts of the universe. One of these void galaxies has received particular attention. It goes by the catalog designation MCG plus 01-02015, a string of numbers and letters that tells astronomers where to point their telescopes but does nothing to capture the profound loneliness of this object. When the Hubble Space Telescope turned its gaze toward this galaxy, it captured an image of a beautiful spiral structure, with graceful arms winding out from a bright central core. It looks, in many ways, like a picture-perfect example of a spiral galaxy, similar to how we imagine the Milky Way might look from outside. But what makes MCG plus 01-029015 so remarkable isn't how it looks, it's where it is. The European Space Agency, in describing this Hubble observation, called it the loneliest of galaxies, a poetic description that captures something essential about its situation. This galaxy is so isolated that if intelligent beings lived there, if they looked up at their night sky with telescopes, they would see almost nothing beyond their own galaxy. No nearby galactic neighbors, no rich clusters of galaxies, just the faint distant glow of galaxies hundreds of millions of light years away at the void's edges. How such a galaxy came to be in such a lonely place remains a mystery. Was it born there, formed from gas that somehow remained in the void while most matter drained away to denser regions? Or did it fall into the void from the surrounding regions, perhaps ejected by gravitational interactions with other galaxies? Neither explanation feels entirely satisfying, and the truth may be something we haven't yet imagined. The 60 void galaxies aren't randomly scattered throughout the Boötes Void. Instead, they're arranged in a peculiar tube-shaped region running through the middle of the void. Imagine the void as a sphere, and then imagine a cylinder or thread running through its center, and that's where the galaxies are. This arrangement has puzzled astronomers since it was first discovered. Why would galaxies line up this way? What could create such a structure? One possibility is that this tube represents a filament of the cosmic web that somehow survived in the void, a thread of slightly higher density that allowed some galaxy formation to occur. Another possibility is that the galaxies mark the axis of rotation of the structure that created the void in the first place, though this raises more questions than it answers. The truth is, we don't fully understand why the void galaxies are arranged the way they are. And this mystery adds another layer to the enigma of the Boötes Void, the cosmic web, nature's grand architecture. To understand why the Boötes Void exists, why it's so empty while other regions of space are rich with galaxies, we need to step back and look at the largest structures in the universe. We need to understand the cosmic web. When you look at a map of all the galaxies in a large volume of space, an extraordinary pattern emerges. Galaxies aren't scattered randomly like salt thrown across a table. Instead, they arrange themselves into an intricate three-dimensional pattern that looks remarkably like a spider's web, or perhaps like the foam in a bubble bath or the structure of a sponge. Long filaments of galaxies stretch across hundreds of millions of light years, connecting dense knots where galaxy clusters congregate. Between these filaments lie the voids, vast empty bubbles in the cosmic foam. This cosmic web is one of the largest and most beautiful structures in nature. It spans the entire observable universe, billions of light years in every direction, and it represents the end result of more than 13 billion years of cosmic evolution. But the cosmic web wasn't always so apparent. Through most of the 20th century, astronomers knew that galaxies clumped together in groups and clusters, but they thought these structures were more or less randomly distributed through space. The idea that there was a coherent large-scale structure, a pattern to the distribution of galaxies, emerged only gradually as astronomers conducted larger and deeper surveys of the sky. One of the first hints came in the 1970s and 80s when astronomers began measuring the distances to large numbers of galaxies. These redshift surveys, like the one that led to the discovery of the Boötes Void, allowed astronomers to create three-dimensional maps of the universe. When they plotted galaxies in 3 dimensions rather than just mapping their positions on the sky, the web-like structure became unmistakable. In 1989, astronomers Margaret Geller and John Huschra at the Harvard-Smithsonian Center for Astrophysics published one of the most famous early maps of large-scale structure. They had measured the distances to thousands of galaxies in a slice of sky, and when they plotted these galaxies in 3 dimensions, they saw galaxies arranged in walls and filaments surrounding great voids. One particularly prominent feature, a long curved string of galaxies they dubbed the Great Wall, a cosmic highway of galaxies stretching across their survey region. Since then, larger and deeper surveys have mapped the cosmic web in ever greater detail. The Sloan Digital Sky Survey, which began operating in the year 2000, has measured distances to millions of galaxies, allowing astronomers to map the large-scale structure of the universe out to billions of light years. More recent surveys, like the Dark Energy Survey, have examined hundreds of millions of galaxies, creating maps of unprecedented detail and breadth. All of these surveys confirm the same basic picture. The universe is organized into a vast cosmic web, with galaxies strung along filaments and clustered at the nodes where filaments intersect, while voids occupy the spaces between. Remarkably, voids make up about 80% of the total volume of the universe. That's right, 80%. The universe is mostly empty space, with matter concentrated into the filaments and nodes of the cosmic web, like a vast cosmic scaffolding. But what creates this web? Why does the universe organize itself this way, instead of distributing matter more uniformly? The answer lies in the universe's history and in the mysterious substance we call dark matter. The universe began 13.8 billion years ago in the Big Bang, an event that brought space, time, matter, and energy into existence in an unimaginably hot and dense state. In those first moments, in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation. This inflation stretched tiny quantum fluctuations to cosmic scales, creating tiny variations in the density of matter and energy. These variations were incredibly small, differences of only a few parts per 100,000. If you could somehow measure the density of matter at different points in the very early universe, you'd find that most regions had almost exactly the same density, with only tiny, tiny differences from place to place. But these tiny differences were the seeds of all future structure. Regions that were slightly denser than average had slightly stronger gravity, which attracted more matter toward them. As more matter accumulated, their gravity became stronger still, attracting even more matter in a runaway process. Meanwhile, regions that were slightly less dense than average lost matter to the growing dense regions, becoming the voids we see today. But there's a crucial detail in this story. The matter that was doing most of the gravitational pulling wasn't the ordinary matter that makes up stars, planets, and people. It was dark matter. Dark matter is one of the great mysteries of modern cosmology. We can't see it directly because it doesn't emit, absorb, or reflect light. But we know it exists because we can see its gravitational effects. Galaxies rotate too fast for the visible matter they contain to hold them together through gravity alone. Galaxy clusters contain more gravitational mass than can be accounted for by their visible galaxies and gas. The path of light bending around massive objects shows more gravitational lensing than visible matter alone could produce. All of these observations point to the same conclusion. The universe contains a lot of matter that we can't see. Matter that interacts with ordinary matter only through gravity. We call this dark matter, and it makes up about 85% of all the matter in the universe. Only about 15% of the universe's matter is the ordinary matter that makes up stars, planets, gas, and everything we can directly observe. Dark matter played the dominant role in shaping the cosmic web. Because dark matter doesn't interact with light or with itself through any force except gravity, it could begin clumping together earlier and more efficiently than ordinary matter. While ordinary matter in the early universe was still being buffeted by radiation pressure like dust in a wind, dark matter was already collecting in dense halos, forming the gravitational scaffolding along which ordinary matter would later flow. Computer simulations of cosmic structure formation beautifully reproduce the web-like structure we observe. These simulations track the evolution of millions of dark matter particles through billions of years of cosmic history, calculating how they move under each other's gravitational influence. The results show dark matter collecting along filaments, with the densest concentrations at the intersections where multiple filaments meet. These intersections become galaxy clusters, the largest gravitationally bound structures in the universe. The filaments themselves act as highways, channels along which gas flows from the voids toward the clusters. When ordinary matter is included in these simulations, it follows the dark matter, flowing along the same filaments and collecting in the same clusters. The gas cools and condenses in the gravitational wells created by dark matter halos, eventually fragmenting to form stars and galaxies. This is how the cosmic web we see today came into being. Dark matter created the scaffolding, and ordinary matter followed, lighting up the filaments and nodes with billions of galaxies. And what about the voids? In these simulations, the voids are regions that started out slightly less dense than average. As nearby denser regions pulled matter toward themselves, these underdense regions became even emptier. The voids expanded as the universe expanded, growing larger over cosmic time. Crucially, they didn't stop growing. Even today, voids continue to expand, pushed outward by a mysterious force we call dark energy. Dark energy is another cosmic mystery, perhaps even more profound than dark matter. While dark matter's existence is inferred from its gravitational attraction, dark energy is inferred from a repulsive effect, a force that causes the expansion of the universe to accelerate. About 5 billion years ago, the universe's expansion, which had been slowing down under the influence of gravity, began to speed up. Something was pushing space itself to expand faster and faster, overcoming the gravitational attraction of all the matter in the universe. We call this mysterious force dark energy, and it makes up about 68% of all the energy in the universe. Dark matter makes up another 27%, and ordinary matter, everything we can see and touch, makes up only about 5%. We live in a universe dominated by things we don't understand. Dark energy affects voids in a particular way. In dense regions like galaxy clusters, gravity is strong enough to completely overcome dark energy's repulsive effect. These regions are gravitationally bound, and dark energy doesn't cause them to expand. But in voids, where there's very little matter, and therefore very little gravity, dark energy dominates. The voids expand, growing larger and emptier over cosmic time. This means that the cosmic web is not a static structure, it's evolving, with the voids growing larger and the filaments and walls being stretched and thinned. Eventually, in the far future of the universe, the voids will dominate completely. The filaments will be stretched until they break, and the cosmic web will dissolve into isolated islands of galaxies, each cluster alone in an ocean of emptiness. But that's a story for later in our journey. For now, the important thing to understand is that the Boötes Void is part of this grand cosmic structure. It's one bubble in the foam, one of the larger bubbles admittedly, but fundamentally similar to the thousands of other voids that fill the universe. The filaments and superclusters that surround it, the Ursa Major supercluster, the Shapley supercluster, the Hercules supercluster, the Corona Borealis supercluster, and the Boötes supercluster itself. These are the walls of the bubble, the denser regions that border the void. The cosmic web is nature's grandest architecture, a structure that spans billions of light years and billions of years of time. And the Boötes Void is one of its most remarkable features, a testament to the fact that sometimes absence can be as important and as mysterious as presence. How voids form and grow, the formation of cosmic voids like the Boötes Void, is intimately connected to the story of how structure formed in the universe. To understand where voids come from, we need to travel back in time to the universe's earliest moments. In the beginning, immediately after the Big Bang, the universe was unimaginably hot and dense, a seething plasma of fundamental particles. Protons, neutrons, electrons, and photons were all mixed together in a cosmic soup, so hot that atoms couldn't form. The radiation pressure from all those photons was so intense that it kept matter from clumping together. But as the universe expanded, it cooled. About 380,000 years after the Big Bang, the universe had cooled enough for electrons and protons to combine and form neutral hydrogen atoms. This moment, called recombination, changed everything. With electrons no longer free to scatter photons, light could suddenly travel through space unimpeded. The universe became transparent, and those photons have been traveling through space ever since. Today, we detect them as the cosmic microwave background, a faint glow of microwave radiation coming from all directions in the sky, the oldest light in the universe. The cosmic microwave background is remarkably uniform. If you measure its temperature in different directions, you find it's almost exactly the same everywhere, about 2.7 degrees above absolute zero. But not perfectly uniform. There are tiny variations, differences of only a few parts in 100,000, slight fluctuations in temperature that correspond to regions that were slightly denser or slightly less dense than average when the universe was 380,000 years old. These fluctuations are the same quantum fluctuations that were stretched to cosmic scales during inflation, now imprinted on the cosmic microwave background. They are, quite literally, the seeds of all structure in the universe. Every galaxy, every star, every planet, and yes, every void traces its origin back to these tiny variations in density. After recombination, with light no longer providing radiation pressure to keep matter evenly distributed, gravity could finally start its work in earnest. The slightly denser regions began to pull in more matter from their surroundings. The slightly less dense regions lost matter to these growing dense regions. And so began a process that has continued for more than 13 billion years, the rich getting richer and the poor getting poorer. But on cosmic scales, in overdense regions, matter collected, condensed, and eventually collapsed to form galaxies and galaxy clusters. But in underdense regions, something different happened. These regions didn't just stay empty, they actively expanded, pushing outward as the denser regions around them pulled matter away. Over time, these underdense regions became voids, enormous bubbles in the cosmic structure. The process that forms voids is surprisingly straightforward in principle, though the detailed physics can be complex. Imagine a region of space that starts out slightly less dense than its surroundings. The gravitational pull from nearby denser regions acts on the matter in this underdense zone, pulling it outward toward the walls. As matter leaves the void region, its density decreases further, making its gravitational pull even weaker. This creates a feedback effect. Less matter means less gravity, which means even more matter gets pulled away, which decreases the gravity further. Meanwhile, at the edges of the void, where matter is accumulating as it's pulled from the void center and attracted by nearby overdense regions, the density increases. These edges become the filaments and walls we see in the cosmic web today. The void, now nearly empty compared to its surroundings, continues to expand. Not because some force is pushing it outward from within, but because the gravitational pull from the surrounding structure is pulling its edges outward, stretching the void larger and larger. Computer simulations of void formation beautifully illustrate this process. In these simulations, cosmologists start with a nearly uniform distribution of dark matter particles representing the early universe, with tiny density variations matching what we see in the cosmic microwave background. They then let gravity do its work, calculating how each particle moves under the gravitational influence of all the others, and watching as billions of simulated years pass. In the early stages, just a few 100 million years after the Big Bang, the structure is subtle. There are slight overdensities and underdensities, but the universe still looks fairly uniform on large scales. But as time progresses, the structure becomes more pronounced. The overdense regions grow denser and more compact. The underdense regions expand and empty out. By the time the simulation reaches an age equivalent to our universe today, the cosmic web is fully formed, with its characteristic pattern of filaments surrounding voids. One fascinating aspect of void formation is that voids can merge. Just as galaxies can collide and combine to form larger galaxies, voids can grow into each other, creating supervoids, enormous empty regions even larger than typical voids. The Boötes Void might be an example of such a supervoid, formed by the merger of several smaller voids over billions of years. There's also the question of why some voids are larger than others. The answer lies in the initial conditions, in those tiny density variations that were imprinted on the universe during inflation. Regions that started out with slightly larger underdensities had a head start in the race to become voids. They could grow larger before their expansion was slowed by the gravitational pull of surrounding structure. The Boötes Void likely started from an unusually large underdensity in the early universe, giving it the opportunity to grow to its current enormous size. But voids don't expand forever at the same rate. In the early universe, when matter was more evenly distributed and the universe was denser overall, voids grew relatively slowly. The gravitational pull from the surrounding matter was strong enough to resist the void's expansion. But as the universe aged and expanded, as matter became more concentrated in filaments and clusters, the voids found themselves with less and less matter to slow their expansion. Then, about 5 billion years ago, something changed. The expansion of the universe, which had been slowing down under the influence of gravity, began to accelerate. This acceleration is attributed to dark energy, that mysterious component making up about 68% of the universe's total energy. Dark energy acts like a repulsive force, pushing space itself to expand faster and faster. Dark energy affects voids in a particular way. In dense regions like galaxy clusters, gravity is strong enough to completely overcome dark energy's repulsive effect. These regions remain gravitationally bound, and dark energy doesn't cause them to expand. But in voids, where matter is sparse and gravity correspondingly weak, dark energy dominates. The voids expand even faster, growing larger and emptier as time goes on. This means that as the universe ages, voids will come to dominate more and more of space. The filaments and walls of the cosmic web are being stretched thinner as the voids they surround grow larger. Eventually, in the far future, the voids will have expanded so much that the filaments will break apart, and the cosmic web will dissolve into isolated clusters of galaxies, each one alone in an ocean of emptiness. But that's a story we'll return to later. The formation of the Boötes Void follows this same general pattern, but the details remain mysterious. Why is it so large compared to other voids? Why are there 60 galaxies within it, arranged in that peculiar tube-like structure? These questions touch on some of the deepest puzzles in cosmology. One possibility is that the Boötes Void represents an extreme statistical fluctuation, a region that just happened to start out with an unusually large underdensity and grew to exceptional size. In a universe as large as ours, containing countless voids, it's not surprising that some would be larger than others. The Boötes Void might simply be on the extreme end of the size distribution. Another possibility involves the details of structure formation in this particular region of space. Perhaps the surrounding superclusters, the walls of the void, formed earlier or more efficiently than average, pulling matter out of the void region more effectively. Or perhaps the void experienced unusual dynamics early in its history, perhaps merging with multiple smaller voids to reach its current size. The 60 galaxies within the void present their own puzzle. Standard models of galaxy formation predict that voids should be almost completely devoid of galaxies. The low density of matter in voids means there is very little raw material from which to build galaxies, and what little matter there is tends to be pulled toward the void walls, where density is higher and conditions are more favorable for galaxy formation. So why are there any galaxies in the Boötes Void at all? Several explanations have been proposed. One is that these galaxies formed in small filaments or slightly denser regions within the void, threads of matter that resisted being pulled completely into the surrounding walls. Another is that some of these galaxies might have formed before the void fully developed, when the region was less underdense and then survived as the void expanded around them. A third, more speculative possibility is that some void galaxies might have fallen into the void from the surrounding regions, perhaps ejected by gravitational interactions with other galaxies or by the disruptive forces during galaxy cluster formation. If this is true, then void galaxies might be refugees, exiles from denser regions who now find themselves in the emptiest places in the universe. The galaxies that shouldn't be there, the 60 galaxies residing in the Boötes Void, are, in many ways, the most intriguing aspect of this cosmic enigma. They shouldn't really exist, or at least they shouldn't exist in the numbers they do. And yet, there they are, defying our expectations, offering astronomers a unique laboratory to study galaxy evolution in the most isolated environments in the universe. Void galaxies, as astronomers call them, are fundamentally different from galaxies in denser regions of space. They evolved in environments largely free from the gravitational harassment that shapes galaxies elsewhere in the universe. In galaxy clusters, galaxies frequently pass close to each other, their mutual gravity distorting their shapes and stripping away gas. They collide and merge, creating new galaxies from the wreckage of old ones. The hot gas that fills galaxy clusters can strip galaxies of their own gas through a process called ram pressure stripping, shutting down star formation and leaving behind dead, red galaxies. But in voids, none of this happens, or at least it happens far more rarely. Void galaxies are cosmic hermits, separated from their nearest neighbors by distances so vast that interactions are exceedingly rare. This isolation means that void galaxies can evolve more peacefully, retaining more of their original characteristics and showing us what galactic evolution looks like when environmental effects are minimized. When astronomers study void galaxies, they find some remarkable differences compared to galaxies in denser environments. Void galaxies tend to be smaller and less massive. They're predominantly spiral galaxies with beautiful rotating disks of stars and gas rather than the elliptical galaxies often found in clusters. They're bluer in color, indicating active star formation, whereas cluster galaxies tend to be redder, their star formation long since shut down. Void galaxies also tend to be gas-rich. They've retained much of their original supply of hydrogen gas, the raw material from which stars form. In denser environments, galaxies can lose this gas through various processes, the ram pressure stripping we mentioned, or tidal interactions with other galaxies, or heating by the hot gas in galaxy clusters. But void galaxies, isolated from these environmental effects, hold on to their gas. This abundance of gas supports ongoing star formation. Studies show void galaxies exhibit higher star formation rates relative to their stellar mass compared to galaxies in denser regions. This makes sense when you think about it. Without environmental processes to shut down star formation, and with plenty of gas available, void galaxies can continue forming new stars at a steady pace. Interestingly, void galaxies tend to experience mergers at later times compared to galaxies in denser environments, resulting in more recent accumulation of stellar mass. This delayed merger history is consistent with the idea that structure formation proceeds more slowly in underdense regions. In voids, galaxies take longer to assemble their mass, growing through a more gradual process than their counterparts in richer environments. The chemical composition of void galaxies also tells an interesting story. Void galaxies tend to have higher gas metallicity, but lower stellar metallicity compared to galaxies of similar mass in denser regions. Metallicity, in astronomical terms, refers to the abundance of elements heavier than hydrogen and helium. These heavier elements are created in stars and distributed through space by supernovae and stellar winds. The pattern observed in void galaxies suggests they're retaining the metals produced by star formation more effectively than galaxies in denser regions, where galactic winds and environmental effects can remove enriched gas. Void galaxies are thought to represent pristine examples of galactic evolution, having few neighbors and likely having formed from pure intergalactic gas. They're closer to the idealized picture of galaxy formation we see in simplified models, where a galaxy forms in isolation from a cloud of gas, without the complications introduced by interactions, mergers, and environmental processes. This makes void galaxies incredibly valuable for testing theories of galaxy formation. When we observe galaxies in clusters and compare them to our models, we're seeing the combined effects of all the processes that shape galaxies, both internal processes like star formation and feedback from supernovae, and external environmental effects. It's hard to disentangle these different effects. But void galaxies let us see what happens when environmental effects are minimized. They're like control groups in a cosmic experiment. Among the 60 galaxies in the Boötes Void, one in particular has captured astronomers' attention. It carries the ungainly catalog designation MCG +01 -02015, but it's earned a more memorable nickname: the loneliest galaxy in the universe. When the Hubble Space Telescope observed this galaxy, it revealed a beautiful spiral structure. The galaxy has a bright central bulge, surrounded by graceful spiral arms, dotted with blue regions of active star formation. In terms of its appearance, it looks fairly unremarkable, similar to countless other spiral galaxies throughout the universe. But its location makes it extraordinary. MCG +01 -02 -015 sits deep within the Boötes Void, separated from its nearest substantial galactic neighbors by tens of millions of light years. Imagine being an intelligent civilization in that galaxy, looking up at your night sky with powerful telescopes. You would see your own galaxy's stars, of course, perhaps hundreds of billions of them spread across your sky. But beyond your galaxy, you would see almost nothing. A few dozen faint, distant smudges of light, other void galaxies separated from you by millions of light years. And beyond them, at the very edge of what you could observe, you might detect the faint glow of the filaments and clusters that wall in your void. On all sides. For beings in such a galaxy, the universe would appear fundamentally different than it does to us. They might develop very different theories about the cosmos. Perhaps they would believe their galaxy was all that existed, with only a few small satellite galaxies as companions. The discovery that there were actually hundreds of billions of other galaxies out there, clustered in filaments and walls beyond their void, would be as revolutionary for them as the discovery of other galaxies was for us in the 1920s. The tube-like distribution of the 60 void galaxies adds another layer of mystery. Why would galaxies arrange themselves in this way? One possibility is that this tube represents a filament of the cosmic web that somehow survived within the void. Even as the void expanded and emptied out, this thread of slightly higher density matter resisted being pulled completely into the walls. Galaxies formed along this filament, creating the linear structure we observe today. Another possibility relates to the dynamics of void formation. As voids expand, they don't necessarily expand equally in all directions. Depending on the surrounding structure, a void might be elongated, stretched longer in one direction than in others. If the Boötes Void is somewhat elongated, galaxies might preferentially survive along its long axis, where the matter density never dropped quite as low as in other directions. A third possibility is that we're seeing a transient phase in the void's evolution. Perhaps the tube of galaxies marks a region where two smaller voids are in the process of merging. The galaxies sit in the boundary region between these two voids, a zone that hasn't yet been fully evacuated. Over the next few billion years, as the void continues to expand and evolve, even these galaxies might be pulled apart or pushed toward the void walls. Galaxies and voids exhibit later morphological types, lower masses, and slower evolutionary rates compared to those in denser environments. This delayed evolution is precisely what we'd expect in regions where structure formation began later and proceeded more slowly due to the lower density of matter. What's particularly fascinating is that even within the void, galaxies aren't completely isolated from their environment. Evidence suggests ongoing assembly through gas dynamics between interacting systems and significant gas accretion, seen in extended gas disks and kinematic misalignments. Some void galaxies show signs of recent interactions or of accreting gas from their surroundings, processes that help them continue growing and forming stars. The study of void galaxies has implications beyond understanding the galaxies themselves. These objects provide a window into the early universe and the processes of galaxy formation. Because structure formation in voids is delayed compared to denser regions, observing void galaxies today might be somewhat like looking back in time, seeing galaxies at an earlier stage of their evolution than we observe in clusters. One intriguing theory about void galaxies involves their role in the larger story of cosmic reionization. After the universe's dark ages, when the first stars and galaxies formed, their ultraviolet radiation began ionizing the neutral hydrogen gas that filled space. This reionization transformed the universe from neutral to ionized, allowing light to travel more freely. Using high-resolution hydrodynamical simulations, researchers showed that photoionization by UV radiation can stop the cooling and collapse of gas in dwarf galaxy halos, particularly in underdense regions like voids. This could explain why voids contain so few galaxies, especially dwarf galaxies. The absence of dwarf galaxies in voids has sometimes been called the void phenomenon, and it represents a test of our models of galaxy formation. Standard cosmological models predict a certain number of dwarf galaxies should exist in voids, based on the distribution of dark matter halos. But observations often find fewer dwarf galaxies than predicted. This discrepancy might be explained by photoheating effects, or it might indicate something about our galaxy formation models needs refinement. As we continue to study the galaxies of the Boötes Void, each new observation reveals more about these cosmic hermits and the extreme environment they inhabit. They challenge our understanding of galaxy formation, test our theories of structure evolution, and remind us that even in the emptiest places in the universe, nature finds ways to create islands of complexity and beauty. Dark energy and the future of voids. The Boötes Void is not just a passive witness to the history of the universe. It is a dynamic, expanding testament to the most mysterious force in existence, dark energy. To truly understand why a gap of 330 million light-years exists, we have to look at the invisible pressure that defines the vacuum itself. In our standard understanding of the cosmos, we often focus on the stuff, the stars, the planets, and the glowing filaments of the cosmic web. But voids like Boötes represent approximately 80% of the total volume of the universe, and it is within these empty bubbles that the true fate of the cosmos is being decided. Dark energy, which makes up roughly 68% of the universe's total energy, acts as a repulsive force that pushes space apart. While gravity works to pull matter together into dense clusters and filaments, dark energy works in the opposite direction, accelerating the expansion of the universe. In a densely populated region of space, the local gravity of galaxies and dark matter is strong enough to counter this repulsive push. However, inside the Boötes Void, there is so little matter that gravity loses its grip. Here, in the great nothing, dark energy reigns supreme, acting as a runaway engine that stretches the void larger and larger every second. This leads us to recent and provocative theories that suggest voids are actually the primary drivers of cosmic evolution. Some cosmologists propose that we cannot understand the expansion of the universe by looking at the average density of space. Instead, we must look at the voids as the dominant features. Because voids are underdense, they expand faster than the rest of the universe. Imagine the universe as a sponge being pulled from all sides. The holes in the sponge grow faster than the fibers. This faster expansion within voids creates a pushing effect on the surrounding walls of galaxies. This is intimately connected to the timescape model, a fascinating alternative to the standard dark energy theory. The timescape model suggests that because gravity affects the flow of time, a concept from general relativity, time actually moves at a different rate inside a massive void compared to inside a dense galaxy cluster. From our perspective, sitting inside a relatively dense region of the cosmic web, the faster expansion and different time flow of distant voids like Boötes create the illusion of a universal dark energy. While this remains a debated alternative, it highlights just how critical these empty spaces are to our understanding of physics. As we look toward the future, the Boötes Void provides a grim preview of what is to come for the entire cosmos. Currently, the cosmic web is a beautiful, interconnected structure of filaments and nodes. But the voids are not static. They are growing, pushed outward by dark energy, and pulled from the outside by the gravity of the surrounding superclusters. Over billions of years, these bubbles will continue to swell. Eventually, the expansion will become so extreme that the filaments of the cosmic web, the bridges of galaxies that connect the universe, will begin to stretch and break. The Boötes Void is essentially a pioneer in this process, having already cleared out 97% of the galaxies that should be there. When we study the void, we are looking at the ultimate winner of the cosmic tug-of-war. Dark energy is thinning out the universe, and the voids are the territory it has already conquered. In the far distant future, every galaxy cluster will be surrounded by a void as vast and empty as Boötes. Until they are so far apart that light from one can never reach the other, the universe will move from a vibrant web of connection to a series of lonely islands in an infinite dark ocean. By measuring the properties of the Boötes Void today, its size, its shape, and a peculiar tube of galaxies at its center, astronomers are trying to calculate exactly how much time we have before the great nothing becomes the only thing. We must immerse ourselves in the silent, invisible mechanics of the vacuum. Dark energy is often described as the cost of having space, a property of the emptiness itself that generates a constant outward pressure. In the dense neighborhoods where we usually reside, this pressure is a mere whisper, drowned out by the thunderous gravitational pull of billions of stars and the massive halos of dark matter that anchor our galaxies. But as we drift into the Boötes Void, the situation reverses. Here, gravity is the whisper, and dark energy is the roar. This region, spanning 330 million light-years, is a place where the density of matter has dropped so low that the cosmic expansion has shifted into a higher gear. It is an accelerated bubble within the universe. When astronomers look at the Boötes Void, they aren't just looking at a gap in a map. They are looking at a region where space itself is being manufactured at a rate that outpaces the ability of gravity to hold things together. This leads us to one of the most compelling and controversial ideas in modern cosmology: the possibility that our standard model of the universe, the lambda CDM model, might be missing a crucial piece of the puzzle that voids are trying to tell us. Some researchers argue that the expansion we see isn't perfectly uniform across the cosmos. Instead, they suggest that the universe is like a loaf of rising raisin bread, where the dough, the voids, is expanding rapidly, while the raisins, the galaxy clusters, remain relatively the same size because they are held together by their own internal gravity. If the Boötes Void is expanding faster than the average part of the universe, it creates a tension in our measurements. This is why the Boötes Void is at the heart of the Hubble tension, the scientific crisis where different methods of measuring the universe's expansion yield different results. By studying how the light from the 60 lonely galaxies inside Boötes is stretched, we can measure the local expansion rate of a dark energy-dominated environment. The timescape model takes this even further, suggesting that our very perception of time is tied to the density of our surroundings. According to Einstein's general relativity, time runs slower in strong gravitational fields. Since a void is a gravitational low point, time there might technically flow at a different rate than it does here in the Milky Way. While this difference is infinitesimally small, when you multiply it across the 330 million light-year span of the Boötes Void, it could significantly alter how we perceive the distance and speed of galaxies on the other side. This would mean that dark energy might not be a mysterious substance at all, but rather a byproduct of our attempt to apply a single uniform clock to a universe that is fundamentally fragmented into dense nodes and vast, empty voids. In this view, Boötes isn't just a hole in space, it's a place where the very rhythm of the universe is different. Furthermore, we must consider the feedback loop that governs the growth of these cosmic deserts. As dark energy pushes the boundaries of the Boötes Void outward, it forces the matter at its edges into even tighter, denser walls and filaments. This creates a rich get richer scenario for gravity at the boundaries, but a poor get poorer scenario for the interior. The matter that remains inside the void is under constant gravitational drainage, being pulled toward the massive superclusters that form the void's walls, such as the Hercules or Corona Borealis superclusters. This drainage reduces the internal gravity even further, which in turn allows dark energy to accelerate the expansion even more. It is a self-reinforcing cycle of emptiness. By understanding this cycle, we can predict the evacuation rate of the universe, how quickly the cosmic web will transition from a connected network into a collection of isolated, dying islands. As we look toward the deep future, the Boötes Void serves as the ultimate foreshadowing. In about 5 billion years, dark energy became the dominant force in our universe, beginning the era of accelerated expansion. We are currently living in the age of voids. Eventually, the expansion will become so powerful that even the light from the superclusters surrounding the Boötes Void will be unable to reach its center. A traveler in the middle of that void would be truly, physically isolated from the rest of the causality of the universe. The study of dark energy through the lens of voids like Boötes tells us that the universe is not just growing, it is disintegrating. Every cubic meter of nothing added to the Boötes Void is a permanent separation between the pieces of the cosmos. Voids are the mechanism by which the universe is being dismantled, and Boötes is simply the largest, most advanced project in that cosmic demolition. Life in the Void, a thought experiment to truly grasp the magnitude of the Boötes Void, we must move beyond the cold, hard data of redshift surveys and enter the realm of human experience. What would it be like to call this immense desert home? The astronomer Greg Aldering once provided a perspective that serves as a chilling anchor for this thought experiment. He noted that if the Milky Way had been located at the center of the Boötes Void, instead of its current position, we wouldn't have known there were other galaxies until the 1960s. This single observation shifts our entire understanding of scientific history and our place in the cosmos. For all of recorded human history, through the rise and fall of ancient empires, the birth of philosophy, the Renaissance, and the Industrial Revolution, our night sky would have looked fundamentally, and perhaps terrifyingly, different. While we would still see the familiar stars of our own galaxy, numbering between 200 and 400 billion, the backdrop against which they rested would be a wall of absolute, unrelenting ink. In our current position within the cosmic web, we have fuzzy patches of light, like the Andromeda Galaxy, which can be seen with the naked eye on a clear night. These smudges of light were the first hints to our ancestors that our galaxy was not the entirety of the universe. They were the breadcrumbs that led us to discover that we live in a vast island universe system. But inside the Boötes Void, those breadcrumbs are missing. There would be no Andromeda to resolve with a telescope, no Triangulum Galaxy, and no Magellanic Clouds dancing in the southern sky. Beyond the outermost stars of our galaxy, there would be no light for millions upon millions of light years. Our first powerful telescopes in the 1920s, like the one Edwin Hubble used at Mount Wilson, would have peered into the darkness and found nothing but more darkness. We would have concluded, with absolute scientific certainty, that our galaxy was a lone spark in an infinite, dead cellar. The profound isolation of such a location would seep into every aspect of a civilization's worldview. For beings living on a planet orbiting a star in the loneliest galaxy, MCG plus 0102015, the universe would appear fundamentally different than it does to us. This galaxy sits so deep within the void that it is separated from its nearest substantial neighbors by tens of millions of light years, a distance that dwarfs even the most expansive structures in our own local group. If intelligent life exists there, their night sky is a lie of omission. They would see their own stars, their own nebulae, and perhaps their own satellite galaxies, but the concept of a cosmic web would be entirely alien to them. They would develop theories of gravity and light based on a sample size of 1. The realization that they were actually surrounded by hundreds of billions of other galaxies, clustered in magnificent filaments and walls just beyond their horizon, would be a psychological and scientific shock far greater than any we have ever experienced. Consider the impact on their early philosophy and religion. Most human mythologies involve the stars and the heavens as a place of infinite activity. But in the void, the heavens would appear as a finite container. Beyond the Milky Way's edge, there would be no reason to believe anything else existed. Their great debate, the astronomical argument over the scale of the universe, would likely have resulted in a consensus that the universe ended where their galaxy's gravity faded. The concept of extragalactic space would be a radical, almost heretical idea, because there would be no visual evidence to support it for centuries of technological development. This isolation isn't just a lack of scenery, it is a lack of connection. In denser parts of the universe, galaxies are constantly interacting. They collide, they merge, and they strip gas from one another in a violent but creative dance that triggers the birth of new stars. Life in the void, however, is a life of cosmic hermetism. The 60 galaxies that do exist within Boötes are refugees or survivors, evolving in a peaceful but stagnant silence. They are smaller, gas-rich, and mostly spiral in shape, having never been battered into elliptical shapes by the gravitational harassment of a cluster. To live in the void is to live in a control group of the universe, seeing what nature produces when it is left entirely alone, free from the messy environment of the cosmic web. If we were to stand on a planet in the center of the void and look out, even with the most powerful telescopes of our early 20th century, the view would be haunting. We would have to wait for the equivalent of our 1960s technology just to detect the faint, distant glow of galaxies at the very edge of the void, over 150 million light-years away. The light reaching us from those walls would have begun its journey before the first dinosaurs even appeared on Earth. We would be looking at a history we didn't know we were a part of. This isolation would likely lead to a much slower development of cosmology as a science. Without the diverse examples of galaxy types found in clusters, our theories on how matter organizes itself would be stunted. We would be like a child raised in a dark room who believes the walls of that room are the boundaries of the entire world. The psychological and sociological impact of such absolute solitude cannot be overstated. In our reality, the night sky has been a canvas for human ambition, navigation, and spiritual inquiry. The smudge of Andromeda, visible to the naked eye, told us that we were part of something larger than ourselves. But for a civilization in the center of the Boötes Void, the sky would offer no such reassurance. They would look up into a dome of stars that ends abruptly at the edge of their own galaxy's gravity. This would create a cultural horizon that is physically and philosophically insurmountable. Their early scientists would likely develop a galactic-centric model of the universe that would be far more difficult to overturn than our old geocentric models. To them, the void would not be a thing to be explored, but the literal end of the world, a cold, empty abyss that represents the finality of existence. Furthermore, consider the technological limitations imposed by this desert. Our understanding of the Big Bang was largely fueled by our ability to see the redshift of thousands of galaxies at varying distances. This data allowed us to realize the universe was expanding. But in the Boötes Void, there are no nearby neighbors to provide this data. With only 60 galaxies scattered across a volume that should contain 2,000, the statistical chance of having a neighbor close enough to study with primitive 20th century telescopes is nearly zero. Their Einstein or Hubble would have no standard candles to measure distance. They would be trapped in a state of scientific dark ages regarding the nature of the cosmos, simply because the universe refused to show them its true face. The loneliest galaxy, MCG plus 0102015, serves as the ultimate case study for this isolation. This galaxy is a beautiful, perfect spiral, yet it is a cosmic hermit. If life exists within its arms, they are living in a pristine environment untouched by the chaotic collisions common in galaxy clusters. While this sounds peaceful, it also means their galaxy is starving. In dense regions, galaxies grow by merging and accreting matter from their neighbors. In the void, there is no one to merge with. Growth is slow, gradual, and fueled only by the meager gas that remains within the galaxy's own gravitational well. It is a life of slow-motion evolution, where the fires of star formation burn steadily, but without the dramatic bursts seen in the bustling cities of the cosmic web. The isolation would also affect their mastery of physics. Much of our understanding of dark matter and dark energy comes from observing how galaxies move relative to one another in clusters. Without those clusters, the missing mass problem might not be discovered for centuries. They would have no way to observe the gravitational lensing that occurs when light from a distant galaxy is bent by a foreground cluster, as there are no foreground clusters to act as lenses. Their science would be built on a foundation of simplicity, but that simplicity would be a mask for the complex reality hiding millions of light years away. When they finally did reach the level of technology required to peer across the 330 million light-year gap, equivalent to our 1960s or 1970s radio and optical telescopes, the discovery would be traumatic. Suddenly, the finite universe would explode into an infinite web of billions of galaxies. The great nothing they believed in would be revealed as just a single empty bubble in a much larger, crowded ocean of light. This great awakening would redefine their history, their religion, and their sense of self. They would realize that for their entire existence, they had been living in the most isolated suburb of the universe, a cosmic Sahara where the silence they took for granted was actually the exception to the rule. As we conclude this thought experiment, we must realize that the Boötes Void is a mirror of our own future. Due to the acceleration of dark energy, every galaxy cluster will eventually become as isolated as MCG plus 0102015. The cosmic web is being dismantled, and one day every sentient being in the universe will look up at a sky that shows them nothing but their own stars. The Boötes Void isn't just a strange place in the sky, it is a preview of the long night that awaits all of us. It teaches us that our current era, filled with visible neighbors in a vibrant cosmic web, is a rare and fleeting gift. We are the lucky ones who can still see the light of other island universes across the dark. Modern observations and ongoing mysteries as we move from the philosophical solitude of a hypothetical void dweller back to the cold reality of 21st century astrophysics, we find ourselves equipped with tools that Robert Kirshner could only have dreamed of in 1981. Today, we no longer look at the Boötes Void as a mere hole in a 2D map. Instead, we see it as a complex, three-dimensional architectural feature of the cosmic web, a vast cathedral of nothingness that we are only beginning to map in high resolution. Modern observations have transformed the Boötes Void from a statistical anomaly into one of the most significant testing grounds for our understanding of the universe. To study it today, astronomers use a multi-messenger approach, combining massive redshift surveys, cosmic microwave background, CMB analysis, and sophisticated computer simulations that attempt to recreate the last 13.8 billion years of cosmic history. The primary way we study the void today is through redshift surveys, such as the Sloan Digital Sky Survey, SDSS, and the more recent Dark Energy Spectroscopic Instrument, DESI. These projects act as the cartographers of the cosmos. By measuring the redshift of millions of galaxies, the way their light stretches as they move away from us, we can determine their exact distance and position in 3D space. When we point these instruments toward the constellation of Boötes, the results are consistently startling. While the surrounding regions are teeming with thousands of galaxies clustered into dense walls and filaments, the interior of the void remains stubbornly empty. However, modern sensitivity has allowed us to find what earlier surveys missed: the cosmic hermits. These are the 60-odd galaxies that somehow defied the gravitational drainage of the void. But as we look closer, a new mystery emerges. These galaxies aren't just scattered randomly like dust motes. They appear to be arranged in a strange thin tube or thread that pierces through the center of the void. This tube structure is one of the greatest ongoing mysteries of the Boötes Void. According to our current understanding of how gravity works on a large scale, matter should be pulled toward the edges of a void, leaving the center completely empty. The existence of an organized thread of galaxies suggests that there might be an invisible subfilament of dark matter running through the void, acting as a bridge. This challenges our standard cosmological models. If the Boötes Void is the result of smaller voids merging together, as many theorists believe, this tube might be the scar left behind from a prehistoric collision of two cosmic bubbles. Studying this structure requires the most sensitive spectroscopic measurements we can achieve, as these galaxies are often small, faint, and isolated, making them difficult targets even for our best observatories. Another modern window into the void is the cosmic microwave background, CMB, the afterglow of the Big Bang. When astronomers look at the CMB, they look for cold spots, regions where the background radiation is slightly cooler than the average. When light from the CMB passes through a massive expanding void like Boötes, it undergoes a process called the integrated Sachs-Wolf (ISW) effect. As the light enters the void, it falls into a gravitational dip, gaining energy. However, because the void is expanding rapidly due to dark energy, by the time the light exits the other side, the gravitational dip has flattened out. The light loses more energy exiting than it gained entering, resulting in a cold spot on our maps. By correlating the maps of the Boötes Void with CMB data, modern scientists can measure the expansion rate of the void with incredible precision. This allows us to use the Boötes Void as a giant lens to study the properties of dark energy itself. Despite these advanced tools, the void phenomenon remains a persistent thorn in the side of standard cosmology. Our best simulations of the universe, such as the Illustris 10G or the Millennium Simulation, predict that even in an under-dense region like Boötes, there should be hundreds, if not thousands, of dwarf galaxies, tiny, dim collections of stars that are the building blocks of larger galaxies. Yet, when we look with our most sensitive instruments, we find almost none. This discrepancy is known as the missing dwarf problem in voids. Where are they? Did they never form, or did something destroy them? Some theories suggest that the intense ultraviolet radiation from the first stars and the surrounding superclusters, a process called photoionization, might have heated up the gas inside the void so much that it could never cool down enough to collapse into dwarf galaxies. In this scenario, the Boötes Void isn't just empty because of gravity. It's empty because it's too hot for small galaxies to be born. The mystery of the Boötes Void deepens when we consider the role of cold spots and the subtle interactions between the void and the light that traverses it. In modern cosmology, we use the Boötes Void as a massive natural laboratory to test the integrated Sachs-Wolf (ISW) effect. As photons from the cosmic microwave background, the afterglow of the Big Bang, enter a region as underdense as the Boötes Void, they fall into a shallow gravitational potential well. In a static universe, these photons would regain their energy as they climb out of the other side. However, because dark energy is actively stretching the void while the light is passing through it, the gravitational well becomes even shallower by the time the photons exit. This causes the photons to lose more energy than they gained, leaving a detectable cold imprint on our sky maps. These observations provide a direct measurement of the expansion rate inside the void, confirming that these cosmic deserts are the fastest growing regions in the universe. However, the more data we collect, the more the Boötes Void seems to defy our standard cosmological simulations. High-resolution hydrodynamical simulations, like those used to study galaxy formation, suggest that even in an underdense environment, gravity should still be able to pull together enough gas to form thousands of dwarf galaxies. Yet, our observations consistently find a void phenomenon, a significant deficit of these small, dim galaxies compared to our theoretical predictions. This discrepancy suggests that either our understanding of dark matter scaffolding is incomplete, or there is a powerful feedback mechanism at play. One leading theory is that the rionization of the universe, the period when the first stars lit up and stripped electrons from neutral hydrogen, happened more aggressively in or around these voids, heating the gas to a point where it could no longer collapse into small star-forming regions. The tube of galaxies running through the center of the void presents another layer of complexity for modern researchers. This structure is not just a random alignment. It appears to be a filamentary survivor. Some astronomers hypothesize that we are witnessing a transient phase in the life of the void. It is possible that the Boötes Void was originally 2 or 3 smaller voids that merged. The tube of galaxies we see today might be the residual matter caught in the boundary between those merging bubbles, a thin thread of gas, and stars that hasn't yet been fully evacuated into the surrounding supercluster walls. If this is true, the Boötes Void is much more than a simple hole. It is a dynamic collision site of cosmic scale proportions. As we look toward the future, the James Webb Space Telescope, JWST, and upcoming missions like the Euclid Space Telescope are expected to revolutionize our view of this region. While the original discovery in 1981 found only 1 galaxy and subsequent surveys brought the total to 60, we are now searching for the hidden population of the void. We are looking for faint, infrared bright dwarf galaxies and isolated gas clouds that have remained invisible to optical telescopes. These pristine objects would be of immense value, as they represent the most unspoiled matter in the universe, having never interacted with the dense environments of galaxy clusters. The ongoing mystery of Boötes ultimately challenges the cosmological principle, the idea that the universe is the same in every direction and at every location. If a structure as large and empty as Boötes can exist, it suggests that the seeds of the early universe, those tiny quantum fluctuations, were capable of producing much more extreme variations than we previously thought. We are left with a haunting question. Is the Boötes Void a rare statistical fluke? Or are there even larger, deeper voids hiding in parts of the sky we have yet to map? As we continue to refine our maps of the cosmic web, the Boötes Void stands as a reminder that the nothing between the stars is just as complex and mysterious as the stars themselves. The superclusters that currently define the boundaries of the void, the Hercules, the Corona Borealis, and the Shapley superclusters, will themselves succumb to the expansion. Because these structures are so vast, the gravity holding them together is relatively weak compared to the overwhelming repulsive force of dark energy acting across such immense distances. As a result, even these massive walls will fragment. Galaxies will be pushed away from each other at speeds that eventually make communication and travel between clusters impossible. What remains will be a universe of island universes. Each galaxy cluster that is sufficiently bound by its own internal gravity will become a lonely island in an infinite black ocean of nothingness. For a civilization living in one of these future clusters, the Boötes Void's current state of isolation will be their everyday reality. They will look out into the night and see only the stars of their own local neighborhood. The light from other clusters will be stretched so far into the red end of the spectrum that it will eventually become undetectable. The cosmic web, once a testament to the interconnectedness of all matter, will have been replaced by a silence so profound that it dwarfs the human imagination. The Boötes Void is, in essence, a preview of this big freeze. It shows us what happens when the nothing wins. Currently, the void still contains 60 galaxies, 60 holdouts that represent the last remnants of a disappearing structure. But as time progresses, even these void galaxies will be pulled apart or pushed toward the receding horizons. The peculiar tube of galaxies that currently pierces the void's heart will eventually dissipate, its members lost to the ever-growing darkness. This future is one of absolute entropy. As the voids grow to occupy nearly the entire volume of the universe, the density of matter will drop to near zero. The energetic processes that define our current universe, the birth of stars, the collision of galaxies, the flow of gas along cosmic filaments, will cease. The universe will enter a state of permanent cosmic winter. The Boötes Void is a window into this final chapter, a place where the Sahara of space has already arrived. Understanding the future of the void also helps us understand the fundamental nature of existence. It reminds us that the complex structures we see today are transient. The Milky Way and Andromeda will merge to form Nilkameda. But even this giant new galaxy will eventually find itself utterly alone. This vast expansion process will not be limited to galaxies simply drifting apart. It will fundamentally disrupt the entire thermodynamic balance that binds the fabric of the universe together. The expansion of the Boötes Void is a rehearsal for the absolute victory of dark energy. In our universe today, matter and energy are somewhat safe under the protective arms of gravity. However, in the future, when these void waves begin to batter the boundaries of galaxy clusters, it will become impossible even for interstellar gas to condense. When the majestic webs of the cosmic web break, the universe will cease to be an interconnected system as it once was, and will be divided into completely alien, disconnected cells. This unstoppable rise of dark energy is a journey toward the ultimate end of the universe, known as the Big Freeze. The Boötes Void is the precursor to this freeze. In this scenario, also called heat death, all energy differences in the universe will equalize, and the flow of energy required for anything new to form will stop. As voids grow, the total density of the universe drops so low that the hydrogen clouds needed for the birth of new stars can no longer come together. The 60 lonely galaxies inside Boötes are currently experiencing this future firsthand. They are like cosmic candles that cannot be fed from the outside and will burn out one by one after consuming their own fuel. For future observers, the universe will seem like a much smaller place. Today, with Hubble and James Webb, we can see billions of light years away and hear the cosmic background radiation. But in that era, when the voids have won, even light will not be able to keep up with the speed of the expanding space. Photons coming from other galaxies will never reach their destination because the space between them is growing so fast. This is not just a distance problem. It is physical isolation. Every galaxy will turn into a prison surrounded by its own event horizon. The Boötes Void is the first construction site showing us how these prison walls are built. In this process, the stars inside the galaxies will continue to age. The largest stars will explode as supernovae, while the smallest ones will burn slowly for trillions of years and eventually turn into white dwarfs or black dwarfs. As the void expands and cools, matter will no longer be a tool of creation, but merely a remnant. The deep silence that the Boötes Void offers us today will actually be the only song of the universe in the future, the melody of an absolute nothingness. According to an interesting theoretical approach, if dark energy turns into a form of phantom energy that is stronger than we expect, this void expansion could even tear galaxies apart. In this scenario, called the Big Rip, the void not only opens the gap between galaxies, it enters into galaxies' solar systems and even atoms, tearing everything apart at the subatomic level. The Boötes Void is the most prominent footprint of this destructive power in the universe today. This abnormal growth rate shown by the void today is the biggest key for us to understand the nature of dark energy. In conclusion, looking at the Boötes Void is not just looking at a map of the past, but looking at the last page of the universe. Matter and light are short-term guests in the face of darkness and nothingness. The cosmic future is a story not of existence, but of absence. However, this situation should not scare us. On the contrary, it should remind us how rare and precious that star-filled sky we see today is. We are the lucky creatures living in that short but bright parenthesis where the voids have not yet completely won and the cosmic web is still alive. Closing reflections and call to action. As we drift back from the silent depths of the Boötes Void, we are left with a profound sense of the universe's scale and the fragile beauty of our own existence. The great nothing is not just a gap in a map. It is a cosmic mirror that reflects the reality of a universe defined as much by what is missing as by what is present. It challenges our primal intuition that space must be filled with light and matter, reminding us that 80% of our cosmos consists of these vast, underdense bubbles. The Boötes Void teaches us that even in the most extreme deserts of the vacuum, complexity finds a way to survive. The 60 galaxies floating in that ocean of nothingness, arranged in their mysterious, thread-like alignment, stand as a testament to the resilience of structure against the overwhelming push of dark energy. This journey through the void reminds us that we are living in a privileged moment of cosmic history. We inhabit a vibrant neighborhood of the cosmic web where the connections between galaxies are still visible and the secrets of the Big Bang can still be decoded. If our home were the loneliest galaxy, MCG plus 0102015, our understanding of the universe would be shrouded in a darkness that might have taken centuries more to pierce. The void is a silent teacher, showing us that our perspective is shaped by the light we can see. But the truth of the universe often hides in the shadows. As we close this chapter of our cosmic exploration, let the silence of the Boötes Void settle over you. It is a place of profound peace, a cosmic cathedral that hums with the mysteries of dark energy and the slow, steady birth of stars in isolation. It reminds us that every spark of light in our night sky is a precious rarity in a universe that is increasingly leaning toward the dark. If you found this journey through the great nothing as captivating as I have, please consider supporting the channel. By liking this video and subscribing to the Science Pillow, you help us continue to explore the most distant and mysterious corners of our universe. What do you think lies at the heart of the Boötes Void? Could there be more than just those 60 galaxies hiding in the dark? Share your thoughts in the comments below, and let's continue to drift through the stars together.